Two German men, nearly 100 kilometers apart in the same year, 1885 and 1886, invented the exact same thing independently. Karl Benz in Mannheim, Gottlieb Daimler in Cannstatt. They never met, not once, despite living close enough that one could have walked to the other's workshop in 2 days. Yet they both looked at a factory machine designed for textile looms and thought, what if this ran a carriage? Here's the paradox. The internal combustion engine was already 30 years old. It was a stationary thing. It lived in factories. Etienne Lenoir invented the first commercial version in 1860, room-sized, burning illuminating gas from street lamp systems, powering water pumps and textile machinery. For a quarter century, no one imagined putting wheels under it. Then suddenly, two engineers, 100 kilometers apart, simultaneously had the same obvious idea. The mechanism wasn't new. The innovation was absurd, mounting an old factory tool on wheels. To understand why it took 25 years for someone to put a factory engine on wheels, you need to see what came before. For most of the 1800s, factories ran on steam. Huge boilers, massive engines, reliable but slow to start. Water wheels worked if you lived near a river. Animals worked for small operations. Nothing was portable. Nothing was high-powered density. In 1680, the Dutch physicist Christian Huygens conceived of a gunpowder engine, explosive force driving a piston. The idea was theoretically elegant. Huygens never built it. For 180 years, no one acted on it. Then, in 1860, Etienne Lenoir, a Belgian-born engineer working in France, filed a patent for the first commercially viable internal combustion engine. It burned coal gas, the same illuminating gas that lit Paris streets, 1 horsepower, room-sized, produced about 4 to 5% thermal efficiency. Lenoir's invention was crude, but it worked. By 1870, 1,000 Lenoir engines existed across Europe. They powered printing presses, sawmills, textile machines. Every factory owner recognized the appeal. More compact than steam, no boiler to heat, no water required. But the thought never occurred to anyone, what if this powered a vehicle? The mechanism was the problem. It was inefficient, it was unreliable, and crucially, there was no fuel infrastructure. Gasoline didn't even exist yet. It was considered waste. In 1876, Nicholas Otto, a German engineer, solved the efficiency problem. He invented the 4-stroke cycle. Intake, compression, power, exhaust. Compressed the fuel mixture before ignition, quadrupled the thermal efficiency to 12 to 15%. Otto's design was patented, it was licensed. Over 30,000 Otto cycle engines were manufactured between 1876 and 1886. The technology was proven, reliable, efficient, and still, no one mounted it on wheels. Then, in 1885 and 1886, within months of each other, Karl Benz and Gottlieb Daimler each built the same realization. Benz worked in Mannheim, a machine tool manufacturer. Daimler and his partner Wilhelm Maybach worked in Cannstatt, about 95 kilometers away. Neither knew what the other was doing. Benz filed patent 37,435 on January 29, 1886. His patent motor wagon had 3 wheels, a single-cylinder Otto engine, and a chassis designed from scratch. Not a horse carriage adapted, but a vehicle engineered for powered propulsion. Maximum speed, 16 kilometers per hour. Daimler's right wagon arrived months earlier, a motorcycle-like design with 2 wheels, a smaller engine, even slower. First test, November 1885. Daimler's 17-year-old son, Paul, rode it. A small fire erupted midway. Paul extinguished it and completed the journey. But the parallel invention reveals something crucial. The idea was obvious once the preconditions existed. Otto cycle invented, gasoline availability growing, machine manufacturing capacity everywhere. The insight wasn't genius, it was inevitability. 2 engineers, 100 kilometers apart, independently reached the same inevitable conclusion. Then, in 1888, something unexpected happened. Bertha Benz, Karl's wife, took the patent motor wagon without permission and drove it 106 kilometers from Mannheim to Pforzheim, first long-distance automobile journey. She stopped at a shoemaker's workshop to repair the brakes. When she arrived in Pforzheim, she proved something her husband couldn't. The car wasn't just an experiment, it had practical value. By 1900, the American automobile market had three competing technologies: 40% steam powered, 22% gasoline, 38% electric. Electric cars seemed obviously superior, silent, no hand crank required, smoother acceleration, safer. Women preferred them because you didn't risk a broken arm, cranking a gasoline engine to start. Columbia Electric was the largest manufacturer. Studebaker made elegant electric carriages. Detroit Electric marketed itself as the ladies' car. Electric cars had 30 to 40-mile range per charge, adequate for urban distances and poor quality roads. Gasoline cars were faster but dangerous. Hand starting could be violent, explosions were frequent, reliability was terrible. If you predicted the winner in 1900, you would have said electric. Then on January 10th, 1901, everything changed. Near Beaumont, Texas, a salt dome called Spindletop erupted. At 1,139 feet depth, the Lucas well struck one of Earth's largest oil reservoirs. The pressure was so high that oil erupted 150 feet into the air. A single well flowed 100,000 barrels per day for 9 days straight. This was more oil in a week than all of North America had produced in the previous decade. Oil price collapsed. $1.50 per barrel in 1900 became 30 cents by 1902. Gasoline, which had been expensive waste, suddenly became abundant and cheap, cheaper than water. Now the paradox crystallizes. In 1900, electric cars were technically superior. They lost not because they were inferior, they lost because a single geological accident made gasoline free. In 1908, Henry Ford introduced the Model T at $850. By 1913, the assembly line production method was revolutionary. Assembly time dropped from 14 hours per car to 1.5 hours per car. Price collapsed. $850 became $600, then $350. By 1925, the price was $260. A factory worker could now buy a new car for 8 months of wages. The automobile transitioned from luxury item to commodity, but only the gasoline car could achieve that price point. Electric cars required expensive batteries. They couldn't compete on cost. Meanwhile, there was the Selden patent. George Selden, a patent attorney, had filed a broad claim in 1879 for a road engine using internal combustion. Patent 549,160, granted in 1895. Selden never built a car, never even tried. But he formed the electric vehicle company and demanded licensing fees from every automaker, claiming they infringed his patent. Henry Ford refused to pay. 8 years of litigation followed, 14,000 pages of testimony. By January 10th, 1911, exactly 10 years to the day after Spindletop, a federal appeals court ruled in Ford's favor. The court determined that Ford's Otto cycle engine was fundamentally different from Selden's Brayton cycle design. Selden's patent was destroyed. Ford became a folk hero for defeating the patent troll. The victory accelerated his expansion. Mass production of gasoline cars continued unchecked. The choice had been locked in. But while Spindletop made gasoline cheaper than water, this episode is brought to you by a private community I run. A community where I break down 100,000 deep dive courses on how systems evolved, how better technologies lose, and how geological accidents reshape civilization for centuries. If you've watched a technically superior alternative lose to a cheaper accident, the full deep dives explore how path dependence gets locked in, why electric cars still haven't recovered a century later, how Spindletop created geopolitical addiction. Link is in the description below. And now back to the century built around a controlled explosion in a metal cylinder. The reversal took 123 years. In 2008, Tesla released the Roadster with 200-plus mile range per charge and lithium-ion batteries that were light and dense enough to make an electric car actually desirable. Tesla proved something the market had forgotten. Electric cars could be fast. Tesla proved they could be desirable. The Roadster did 0 to 60 in 3.9 seconds. Suddenly, EV didn't mean compromise. By 2024, electric vehicles represented 19.9% of global new car sales. Lithium-ion battery costs fell 85% from 2010 to 2024. Energy density doubled. Charging time compressed to under 5 minutes for 80% charge. In China, new energy vehicles, battery electric plus plug-in hybrids, reached 50% of new car sales in 2025. The first year, EVs exceeded internal combustion. the first year in 123 years where the better choice wasn't locked out by geological accident. Yeah, here's what the ice paradox cost. Today, approximately 1.4 billion internal combustion vehicles operate on Earth. They produce about 16% of global carbon dioxide emissions. The transportation system built around a factory machine has become the operating system of modern civilization. Annually, 1.3 million people die in car accidents. That's the toll of moving from point A to point B in an explosion driven carriage, a design inherited from factory machinery. In 1921, Thomas Midgley Jr., a chemist at General Motors, discovered that tetrethyl lead eliminated engine knock. It allowed higher compression ratios, greater power, more efficiency. Starting in 1923, leaded gasoline became universal. Ethyl brand. Sold everywhere, but lead accumulated. Atmospheric lead increased 800 times between 1900 and 1980. An estimated 68 million American children born between 1923 and 1986 experienced lead poisoning from gasoline fumes. Reduced IQ, behavioral damage, academic decline. Lead wasn't removed from U.S. gasoline until 1986, 63 years of poison. The cost still accumulates in soil and dust and memory. Three deep lessons hide in the ice paradox. First, technological lock-in doesn't require superiority, only alignment. The internal combustion engine didn't win because it was fundamentally better. It won because Spindletop happened to produce cheap fuel at the exact moment when automobile markets were forming. One geological event in one place at one moment locked an entire global civilization into a mechanism for 123 years. Second, better alternatives don't matter if the cheaper accident comes first. Electric cars were objectively superior in 1900. Quieter, safer, cleaner, more enjoyable to operate. Yet they vanished by 1930. Path dependence doesn't care about superiority, it cares about timing and cost. Once you've built 100,000 gasoline cars and a distribution network for gasoline and roads designed for gasoline range, the choice becomes irreversible. The system feeds itself. Third, the cumulative cost of technology lock-in only becomes visible decades later. In 1901, no one imagined that a cheap oil field would reshape geography for a century. No one anticipated suburban sprawl, oil geopolitics, air pollution, climate change, lead poisoning of generations, 14 billion automobile deaths through 2024. These consequences were outside the decision-making frame. They accumulated in the background while the system optimized for cost and speed. That vintage brass engine valve with verdigris patina, the candlelit macro of a single oil drop on machined copper, could have remained a factory machine. Lenoir imagined it powering looms. Otto imagined it powering everything stationary. But two engineers 100 kilometers apart had the same thought. And Texas had the misfortune of sitting on too much oil and a century of civilization piled on top. The mechanism itself was indifferent to purpose. A lock designed for factory work protected corporate supply chains equally well. Mounted on wheels, suddenly it reshapes continents. The tool doesn't care. The technology doesn't distinguish between the purposes it serves. Every ordinary technology hiding inside civilization came from a problem you'll never face, the four-stroke cycle you inherit from factory machinery. The fossil fuel you combust came from geological chance, and the choice to build an entire world around controlled explosions came from an accident no one could have predicted.